A recurrence or a recurrence relationship is a equation or inequality that describes a recursive function in terms of its input. This equation or inequality in most of the cases represent the time or space complexity of the function. Let us take example of the recursive factorial function that we saw in the previous lesson. From the previous lesson, we know that the time complexity of this function is order of n. And we have used the function called tree or the memory model to find the time complexity. How we did was that first this function is called for n. From inside this function, the function is called for value n minus 1. From inside this function, the function is called for n minus 2 and so on. We keep on calling the function until the value of n reaches 1. When the value of n reaches 1, then we stop and start returning. It means that the function is called n times. Now every time the function is called, it will take some constant time because inside the function we are just performing a condition check and a multiplication. Therefore the total time taken is n times some constant which is order of n or big O of n. Another way of looking at this time complexity is that you draw the memory model and see how the functions are getting called. From the memory model also you will be able to conclude the same thing, that because the function is called n times and each time the function is called it will take some constant time, therefore the time complexity of the function is big O of n or n into some constant. Here we want to represent the time taken by this function in terms of a mathematical equation. Let's say the time taken by this function is represented by the function t. So t of n represent the total time taken by the fact function for input parameter n. Therefore fact of n minus 1 will take t of n minus 1 time. And because this function is taking constant time, so we can say that t of n, time taken by the factorial function for input parameter n, is equal to time taken by the same function for input parameter n minus 1 plus some constant time which is big O of 1. Now this mathematical equation is representing the asymptotic time complexities. Therefore instead of big O of 1 you can just write 1. Therefore we can say that t of n is equal to t of n minus 1 plus 1. Here this 1 is not the absolute value 1 but some constant, because this equation is representing the asymptotic time complexity and not the absolute time taken by the function. You can also say that the equation of Tn actually should be Tn is equal to t of n minus 1 plus 1 in cases where n is greater than 1, and this is 1 in cases where n is less than or equal to 1. This will incorporate even the terminating conditions. So the equation Tn is equal to Tn minus 1 plus 1 is essentially representing this equation. These two are same. Now how do we solve this equation? There are two ways of solving this equation. One way is that you can use the substitution method. Substitution method means that you substitute the value of Tn minus 1 in terms of Tn minus 2. See, because Tn is defined in terms of Tn minus 1, we can define Tn minus 1 in terms of Tn minus 2. So we can say that time taken by the function for n minus 1 is equal to time taken by the function for n minus 2 plus 1. So this equation becomes time taken for n is equal to time taken by n minus 2 plus 1 plus 1. So plus 1 for this and plus 1 for this. If you extend it further, then we can say that this is equal to t of n minus 3 plus 1 plus 1 plus 1. So 3. Similarly, you can say that this is also equal to t of n minus 4 plus 1 plus 1 plus 1 plus 1 4 times. Or if you keep on doing it, then we can say that this is equal to t of 1 plus 1 plus 1 plus 1 and so on n minus 1 times. Because t of 1 is constant, so this is again 1 plus 1 plus 1 plus 1 n times, and this is equal to n. So when we are saying n, it essentially means n into some constant or big O of n. This is the substitution method. During the coding interviews, you will be finding the time complexity of a method using either the function called tree or the memory model. But in academics, sometimes you are not even given the function, you are just given this recurrence equation. And when you are given this recurrence equation, then you are expected to solve this recurrence equation more mathematically because you does not have a code to back it up. This is a Java code which will print all the elements of the array. What will be the recurrence equation for this recursive function? If the time taken by this function is assumed to be Tn, we can say that time taken by the function for array of length n is equal to time taken by the function for array of length n minus 1 plus some constant. Here the length of the array means the remaining elements of the array which are yet to be printed. You notice that even though the two functions are different, the recurrence equation of these two functions are exactly the same. Similarly, if you want to find the recurrence equation of recursive implementation of linear search or recursive implementation of printing all the elements of a linked list, either in the forward order or in the reverse order, you will find that the recurrence equation will come out to be the same. So if we are able to solve this recurrence equation, we will be able to find the time complexity of all the functions which are represented by this recurrence equation. What do you think is the time taken by this function? Let's assume that this function takes time t of n. Then inside the function, we have a for loop. So this function, so every instance of this function takes order of n time, and then the function calls itself for n minus 1. So it is increasing the count. Let us say the initial value of count is 0. When count becomes equal to n, then we stop. It means that first the function is called for count is equal to 0. Then the function is called for count is equal to 1. Then it is called for count is equal to 2. Then it is called for count is equal to 3, and so on. When the function is called for count is equal to n, then it will just return from here. For every other call, the function prints hello n times. It means that when the function is called for count is equal to 0, the function takes order of n time. When the function is called for count is equal to 1, the function takes order of n time. When the same function is called for count is equal to 2, the function again takes order of n time. Every instance of the function takes order of n time, except obviously the last instance where the function is just returning from here because it is hitting the terminating condition of the recursion. What is the recurrence of this function? In this case, time taken by the function for n is equal to time taken by the function for n minus 1, because we are calling the function, plus big O of n. Let's find the time complexity of this function using both the methods. First, let us find it using the function call tree. Then we will find it using the substitution method. If we draw the function call tree, then function call tree will be very similar to this. That first the function is called for n and count is equal to 0. Then the function is called for n and count is equal to 1. Then the function is called for n and count is equal to 2. In this instance of the function takes n time. In this instance of the function again takes n time. In this instance also the function takes n time, and so on. When the function is called for n minus 1, the function again takes n time. And finally, when the function is called for n, the function takes constant time. It means that the total time taken is summation of all of these times, which is n square. So we can say that t of n is equal to order of n square. What if we have to solve this using the substitution method? So we can say that t of n minus 1 is equal to t of n minus 2 plus order of n. If you substitute this equation, this blue equation, in the black one, we will get t of n is equal to t of n minus 2 plus 2 into n. If you substitute n minus 2 with n minus 3, then this is equal to t of n minus 3 plus 3 into n. You keep on doing it like this until you reach t of 1. So when you reach t of 1, this would have become n into n, which is n square, and t of 1 is constant. So we can say that t of n is some constant plus order of n square. This is equal to order of n square. In both the cases, we are getting order of n square. What if the function is given like this? The recurrence for this function is t of n is t of n minus 1 plus order of n. But here, this n and this n are related. Therefore, t of n minus 1 will be equal to t of n minus 2 plus n minus 1. So we can say that t of n is equal to t of n minus 2 plus n plus n minus 1. If you replace this n minus 2, then t of n minus 2 will be equal to t of n minus 3 plus n minus 2. So this will come out to be t of n minus 3 plus n minus 1 plus n minus 2. So this way, if you expand this entire equation, you will get that t of n is n plus n minus 1 plus n minus 2 plus n minus 3 and so on plus 1. This is summation of n, and you know that summation of n is order of n square. Therefore, even this comes out to be order of n square. Now going further, I will only be writing the recurrence equation of the function, and you can draw the function called tree and validate the time complexity of the function with the function called tree also. What if the recurrence of a function is given to be t of n is t of n minus 1 plus log n? If we use the substitution method, this comes out to be t of n minus 2 plus log of n minus 1 plus log of n. If you expand it further, you will get that this is equal to log of n plus log of n minus 1 plus log of n minus 2 and so on plus log of 1. If we use the logarithmic formulas, this will be log of n into n minus 1 into n minus 2 into n minus 3 and so on up to 1. So this comes out to be log of n factorial. We know that for n factorial, n raised to the power n is upper bound of n factorial. So this is less than equal to log of n raised to the power n, which means n log n. So if you have a recursive function that is calling itself with n minus 1, and inside the recursive function you are taking log n time, then the time complexity of that recursive function will be n log n. This is true for all such recursive functions. This is the benefit of having the recurrence relationship, that recurrence relationship is applicable on multiple functions, on all the functions of similar nature. Therefore, if you know the generic formula of solving any recurrence relation, then you just need to find the recurrence of the given code and you will be able to solve that. Now there are two types of recurrences. In this video, we are discussing the first type of recurrence. In the next video, we will be discussing the next type of recurrence. The first type of recurrence are the ones which are decreasing linearly. We have already seen that the solution for this recurrence is Tn is equal to big O of n. What if the equation is like this? You can yourself write a function which corresponds to this recurrence relationship. If this is the recurrence relationship, then 1 will be added n by 2 times instead of n times. Therefore, the time complexity will be n by 2 instead of order of n. You can see that because we are jumping 2 positions at a time, because we are jumping 2 values, only half of the values will get added. In the previous case, 1 is getting added n times. Here 1 will be added only n by 2 times. So if 1 is getting added n by 2 times, then the time complexity will be n by 2, which is again big O of n. What if this equation is Tn is equal to t of n minus 3 plus 1? Again Tn is n by 3, which is also big O of n. Therefore, if the equation is Tn is equal to t of n minus b, where b is any constant greater than 0, plus 1, then we can say that Tn is big O of n. What if the recurrence equation is this? It means that from a function, the function is getting called twice. We can solve it from the function called tree also. The function called tree will be, initially the function is called for n, and at this level we are taking constant time. Then in the next level there are two function calls, each for value n minus 1, and both of them will take constant time. So at this level the total time taken is 2 into constant. In the next level there will be 4 function calls, each with value n minus 2, and each function call will take constant time. Therefore the total time taken at this level will be 4. Similarly, at the next level, there will be 8 function calls and each function call will take constant time. Therefore, the total time taken is 8. So you keep on doing this. We will stop when n becomes equal to 1, which will be after n levels in this function called tree. Therefore, the total time taken will be 1 plus 2 plus 2 square plus 2 cube plus 2 raised to the power 4 plus so on plus 2 raised to the power n. This is a GP series and we know that the sum of GP series is a into r raised to the power n plus 1 minus 1 divided by r minus 1, where r is the common ratio. In this equation, r is 2 and a is 1. So this comes out to be 2 raised to the power n plus 1 minus 1 divided by 2 minus 1, which is big O of 2 raised to the power n. Therefore, this recurrence is exponential time recurrence, 2 raised to the power n. You can also relate it to the exponential growth that we have discussed in the previous lectures. What if the recurrence is Tn is equal to 3Tn minus 1 plus 1? In this case, it will be order of 3 raised to the power n, because now the function is getting called 3 times, and if the first level has 1 node in the function called tree, then the next level will have 3 nodes. Can you solve it using the substitution method? Yes, you can. You just need to replace this Tn minus 1 with Tn minus 2. So Tn minus 1 will be equal to 2 into Tn minus 2 plus 1. This 1 will get multiplied with 2 and it will become 1 plus 1, 2. Then next time it will be 4. Next time it will be 8. Every time Tn minus 1 will keep on decreasing. You will get the same geometric progression that we have got in the function called tree. So whether you solve it using the function call tree or you solve it using the memory model or you solve it using the substitution method of recurrence equation, you will get the same result. Let us recap what we have seen. If the recurrence is like this, then the answer will be big O of n into 1. If the recurrence is like this, then the answer is big O of n into log n. If the recurrence is like this, then the answer is big O of n into n or big O of n square. If the recurrence is like this, then the answer will be big O of n into n square or big O of n cube. So every time what we are doing is, if you have an equation like this, then we are just multiplying this function with n. Therefore, the solution for this recurrence will be that Tn is equal to big O of n into Fn. This is true even when Tn is equal to T of n minus b plus Fn, where b is any constant greater than 0. Therefore, for this kind of recurrence where Tn is equal to T of n minus b plus Fn, the answer will always be order of n multiplied by Fn. You just need to multiply this function with n. We have also seen that the solution for this kind of recurrence is order of 2 raised to the power n. And we have also seen that order of this kind of recurrence, Tn is equal to 3Tn minus 1 plus 1, is order of 3 raised to the power n. So both of these are exponential time complexities. What if we have a recurrence Tn is equal to 2 times T of n minus 1 plus n? In this case, this n will be multiplied with 2 raised to the power n. And this will come out to be big O of 2 raised to the power n into n. You can also validate this using the function call tree or the memory model or the substitution method. Similarly, if you have a recurrence equation like this, Tn is 2 times T of n minus 1 plus log n, then the solution for this recurrence will be 2 raised to the power n into log of n. Can we come up with some generic solution for all kind of equations? Let's say you are given a recurrence equation Tn is equal to a times T of n minus b plus Fn. In this case, obviously a has to be greater than 0 and b also has to be greater than 0. Because if b is equal to 0, then this becomes an infinite recursion. If a is equal to 0, then this doesn't make sense. To solve this kind of generic recurrence, you just need to consider the value of a. There are 3 possibilities. First possibility is that the value of a is less than 1. Second possibility is that the value of a is equal to 1. And third possibility is that the value of a is greater than 1. If the value of a is less than 1, then Tn is big O of Fn. If the value of a is equal to 1, this we have seen, if a is equal to 1, then this becomes Tn is equal to T of n minus b plus Fn. In that case, you just need to multiply Fn with n. So this will be big O of n into Fn. And in the third case, when value of a is greater than 1, then T of n will be exponential. So this will be big O of a raised to the power n divided by b into f of n. This is nothing but the master theorem for this kind of recurrences. In the next lesson, we will see another kind of recurrence where instead of n getting decreased by a constant amount, n will get divided by a constant number.